The vertical columns on the periodic table are called groups or families because of their similar chemical behavior. All the members of a family of elements have the same number of valence electrons and similar chemical properties. The horizontal rows on the periodic table are called periods. An element is identified by its chemical symbol. The number above the symbol is the atomic number. The number below the symbol is the rounded atomic weight of the element. Elements are arranged from left to right and top to bottom in order of increasing atomic number. The number of electrons in a period increases as one moves down the periodic table. Therefore, as the energy level of the atom increases, the number of energy sublevels per energy level increases. In the history of the periodic table, Daubernier's triad were an early attempt to sort the elements into some logical order by their physical properties. In 17, a letter reported John Wolfgang Daubernier's observation of the alkaline earth, namely that strontium had properties that were intermediate to those of calcium and barium. By 1829, Daubernier had found other groups of 3 elements, hence triads, whose physical properties were similarly related. He also noted that some quantifiable properties of elements, for example atomic weight and density, in a triad followed a trend whereby the value of the middle element in the triad would be exactly or nearly predicted by taking the arithmetic means of values for that property of the other 2 elements. Daubernier's triad and Newland's law of octaves were early attempts at classifying elements into groups based on their properties. Since many elements were discovered over the course of 18th and 19th century, the broad classification of elements into metals and non-metals became inefficient. Several experiments were conducted in order to identify elements with similar properties and group them together. In 1869, just 5 years after John Newland put forward his law of octaves, a Russian chemist called Dmitry Mendeleev published a periodic table. Mendeleev also arranged the element known at that time in order of relative atomic mass, but he did some other things that made his table much more successful. Here is a picture of Mendeleev's periodic table. Henry Goin Jeffreys Moseley was an English physicist whose contribution to the science of physics was the justification from physics law of the previous empirical and chemical concept of the atomic number. This stemmed from his development of Moseley's law in X-ray spectra. Moseley's law advanced atomic physics, nuclear physics, and quantum physics by providing the first experimental evidence in favor of Neil Bohr theory. Aside from the hydrogen atom spectrum which the Bohr theory was designed to reproduce. That theory refined Rutherford's and Antonius van den Broek's model, which proposed that the atom contained in its nucleus a number of positive nuclear charges that is equal to its atomic number in the periodic table. This remains the accepted model today. The periodic law states that the physical and chemical properties of the element reoccur in a systematic and predictable way when the elements are arranged in order of increasing atomic number. Many of the properties recur at intervals. When the elements are arranged correctly, the trends in element properties become apparent and can be used to make predictions about unknown or unfamiliar elements, simply based on their placement on the table. Grouping of elements. The S, P, and D block elements of the periodic table are arranged into 18 numbered columns or groups. The elements in each group have the same number of valence electrons. As a result, elements in the same group often display similar properties and reactivity. The 3 broad classes of elements are metal, non-metals, and semi-metals. Across a period, the properties of elements become less metallic and more non-metallic. Location and properties of hydrogen in periodic table. Hydrogen is placed above group 1 in the periodic table because it has ns1 electronic configuration like the alkali metals. However, it varies greatly from the alkali metals as it forms cation more reluctantly than the other alkali metals. Hydrogen also acts as a strong reducing agent like alkali metals and also forms binary compounds with electronegative elements, which resembles the group 1 elements. This is one of the reasons why hydrogen was put in group 1. It is a gas at room temperature. It has one proton and one electron in its one and only energy level. Hydrogen only needs 2 electrons to fill up its valence shell. Find the elements. The periodic table displays the symbol and the names of elements along with information about the structure of their atom. The 4 main groups in periodic table are alkali metals, alkaline earth metals, halogens and inert gases. The alkali metals consist of the chemical elements lithium, sodium, potassium, rubidium, cesium and francium. Together with hydrogen, they constitute group 1, which lies in the S block of the periodic table. Some of the properties of alkali metals are: they are not found freely in nature, they are stored in mineral oil solution, they have low melting points, densities, low electronegativity, and they react easily with halogens. The following figure shows the location of alkali metals in periodic table. Alkaline earth metals. The alkaline earth metals are 6 chemical elements in group 2 of the periodic table. They are beryllium, magnesium, calcium, strontium, barium, and radium. Elements have very similar properties. They are all shiny, silvery white, somewhat reactive metals at standard temperature and pressure. Structurally, they have in common an outer s orbital which is full, that is, this orbital contains its full complement of 2 elements, which the alkaline earth metal radially lose to form cations with charge +2 and an oxidation state of +2. All the discovered alkaline earth metals occur in nature, although radium occurs only through the decay chain of uranium and thorium and not as primordial element. There have been experiments, all unsuccessful, to try to synthesize elements 120, the next potential member of the group. Figure shows the location of alkaline earth metals on periodic table. Transition elements. The IUPAC definition defines a transition metal as an element whose atom has a partially filled d subshell which can give rise to cations with an incomplete d subshell. Many scientists describe a transition metal as any element in the d block of the periodic table, which includes group 3 to 12 on the periodic table. In actual practice, the F block, lanthanide and actinide series are also considered transition metals and are called transition metals. Cotton and Wilkinson expand the brief definition by specifying which elements are included. As well as the elements of group 4 to 11, they add scandium and yttrium in group 3, which have a partially filled d subshell in the metallic state. Lanthanum and actinium, which they consider group 3 elements, are however classified as lanthanides and actinides respectively. English chemist Charles Berry first used the word transition in this context, when he referred to a transition series of elements during the change of an inner layer of electrons from a stable group of 8 to one of 18 and from 18 to 32. These elements are known as the D block. The transition metals have the following physical properties in common. They are good conductors of heat and electricity. They can be hammered or bent into shape easily. Their melting points is liquid at room temperature. They are usually hard and tough. They have high densities. This is the location of transition metals on periodic table. Chalcogens. The chalcogens are the chemical elements in group 16 of the periodic table. This group is also known as the oxygen family. It consists of the elements oxygen, sulfur, selenium, tellurium, and the radioactive element polonium. The chemically uncategorized synthetic element livermorium is predicted to be a chalcogen as well. Often, oxygen is treated separately from other chalcogens, sometimes even excluded from the scope of the term chalcogen altogether due to its very different chemical behavior from sulfur, selenium, tellurium, and polonium. The word chalcogen is derived from a combination of the Greek words, principally meaning copper. The term was also used for bronze, brass, any metal in the poetic sense, ore or coin, and the Latinized Greek word gens, meaning born or produced. Shows the location of chalcogens on periodic table. Halogens. The halogens are grouped in a periodic table consisting of 5 chemically related elements: fluorine, chlorine, bromine, iodine, and acetylene. The artificially created element 117, tennessine, may also be a halogen. In the modern IUPAC nomenclature, this group is called as group 17. The name halogen means salt producing. When halogens react with metals, they produce a wide range of salts, including calcium fluoride, sodium chloride, common table salt, silver bromide, and potassium iodide. Halogens are highly reactive and as such can be harmful or lethal to biological organisms in the sufficient quantities. The figure shows the location of halogens on periodic table. Noble gases. The noble gases, historically also the inert gases, sometimes referred to as aerogens, make up a class of chemical elements with similar properties. Under certain conditions, they are all odorless, colorless, monoatomic gases with very low chemical reactivity. The 6 naturally occurring noble gases are helium, neon, argon, krypton, xenon, and the radioactive radon. Oganesson is rarely predicted to be a noble gas as well or to break the trend due to relativistic effects. Its chemistry has not yet been investigated. The properties of noble gases can be well explained by the modern theory of atomic. Their outer shell of valence electron is considered to be full, giving them little tendency to participate in chemical reactions, and it has been possible to produce only a few hundred gas compounds. The melting and boiling point for a given noble gas or close together differing by less than 10 degrees, that is, they are liquids over only a small temperature range. This is the location of noble gases on periodic table. Trends. Periodic trends are specific patterns in the properties of chemical element that are revealed in a periodic table of elements. Major periodic trends include electronegativity, ionization energy, electron affinity, atomic radii, ionic radius, metallic character, and chemical reactivity. Periodic trends arise from changes in the atomic structure of the chemical elements within their respective periods and groups in the periodic table. These laws enable the chemical elements to be organized in the periodic table based on their atomic structure and properties. Due to the periodic trends, the unknown properties of an element can be partially known. Electronegativity. Electronegativity measures the tendency of an atom to attract a sheer pair of electrons. An atom's electronegativity is affected by both its atomic number and the distance at which its valence electrons reside from the charged nucleus. On the periodic table, the electronegativity generally increases as we move from left to right across a period and decreases as we move down a group. As a result, the most electronegative elements are found on the top right of the periodic table, while the least electronegative atoms are found on the bottom left. In chemistry, ionization energy is the minimum amount of energy required to remove the most loosely bound electron of an isolated neutral gaseous atom or molecule. Moving left to right within a period or upward within a group, the first ionization energy generally increases. As the atomic radius decreases, it becomes harder to remove an electron that is closer to a more positively charged nucleus. The electron affinity of an atom or molecule is defined as the amount of energy released when an atom is attached to a neutral atom or molecule in the gaseous state to form a negative ion. Electron affinity generally decreases down a group of elements because each atom is larger than the atom above it. This is the atomic radius trend. Therefore, electron affinity decreases. Moving from left to right across a period, atoms become smaller as the forces of attraction become stronger. The atomic radius of a chemical element is a measure of the size of its atom, usually the mean or typical distance from the center of the nucleus to the boundary of the surrounding shells of electrons. In general, atomic radius decreases across a period and increases down a group. Across a period, effective nuclear charge increases as electron shielding remains constant. Assalamu alaikum. My name is Rimsha Rafiq and I am from BS Biotechnology Department. Today the topic of my presentation is periodic table. So let's get started. In 1669, German merchant and amateur alchemist Brand attempted to create a philosopher's stone, an object that supposedly could turn metals into pure gold. He heated residues from boiled urine and a liquid dropped out and burst into flames. This was the discovery of phosphorus. In 1809, at least 47 elements were discovered and scientists began to see patterns in the characteristics. In 1863, English chemist John Newlands divided the then discovered 46 elements into 11 groups based on characteristics. In 1869, Russian chemist Dmitry Mendeleev started the development of the periodic table, arranging chemical elements by atomic mass. He predicted the discovery of other elements and left spaces open in his periodic table for them. A periodic table is a table of the chemical elements arranged in order of increasing atomic number, usually in rows, so that elements with similar atomic structure and hence similar chemical properties appear in vertical columns.